Hey, my name is Yian Yin. I'm from Cornell University. So I'm studying science of science. So basically, it's trying to thinking about using scientific approaches, including data science, mathematical models, social science theories, to help us understand, predict, and possibly promote successful scientific discoveries, careers, products, organizations, and so on and so forth. What we've been learning during the past few years of exploration is that to really understand these successes, the key is to not look at these successes, but to the contrary, you want to look at failures. Let me be more specific what I'm talking about here. This is very successful life scientists in the United States, thousands of new citations every year, hundreds of active collaborators. Looking at grant history, also pretty good, 15 R1s and a bunch of other collaborative grants. But what we don't see here is that essentially, if you look at the failure record, what it takes to get there is almost 100 failures just within R1 grant applications. So the way we look at this is that this is like a huge volume of iceberg under the water. If you only look at successes, you are missing the majority of this story. And thinking about this iceberg of the water, these are not random failures. They are actually dependent structure between failures. We build on past failures to do future attempts. So there are interactions, there are complex relationships between these failures. So what we are looking at before your success is not just one or two unfortunate failure. It's a complex dynamical system of failed attempts. And here the question is that if we take a scientific perspective, can we use this self-organized failure dynamics as a predictor for us to learn and predict future successes at a very early stage? Okay, so I'm going to share very briefly about two studies we've been doing in this space. This is a paper we published on Nature a couple of years ago, looking at three very different kinds of failures. NIH failures, when people repeatedly submitting our grants, repeatedly did not get funded until they eventually got it or got, just quit the NIH system. Also thinking about serial entrepreneurs, one startup did not successfully exit, tried again, failed again, so on and so forth. And inspired by this idea that innovation in many cases are not that different from crime, we also look at into 3,000 terrorist organizations where their success can be approximated by fatal attacks. What we see here is that combining these three very different data sets with a simple mathematical model of how we update innovations, we are able to discover pretty universal patterns, early signals of eventual successes. What we are seeing here is that for those who eventually succeeded after repeated failures, the timing of their repeated failures by itself is a remarkably strong predictive signal. Where you see those who eventually succeed after repeated failures are failing faster and increasingly faster every time, which is very unique if you take into the other group, which are people who fail, and eventually did not succeed. They just give up. So what this means is that it's a very strong early signal. And also, if you think about the very popular mantra about failing fast, we are finding some quantitative evidence. But now the key is not to fail fast, but also fail faster and increasingly faster every time. Another interesting we see from the data is that these two groups appear a priori similar, but quickly diverge into two different paths. So we have a model showing that there is indeed a phase transition separating these two groups, just like water at a 33-degree versus ice at a 31-degree. Small variations in their learning strategy translate into huge difference in their career outcomes. We also apply this way of thinking, predicting success based on failures into the community level, thinking about collective progress, a group of scientists or innovators trying to improve our ability to update the records on specific scientific or technology frontier, whether it is, developing high temperature superconductors or whether it is providing some high accuracy predictions for specific AI benchmark. What we are seeing here again is that the key here is that if you only look at the state-of-the-art algorithms, it is very hard to find a lot of regularity. But once again, when you bring into all approaches, not only those who are successful, but only those who are also unsuccessful, then immediately we are able to compile millions of records, allowing us to uncover a wide set of universal regularity of empirical frontier dynamics. This includes a correlated basis in terms of both long stages of no progresses, as well as short periods of rapid progresses, which is again uncovered by a simple yet general mathematical framework. So let me conclude here by saying that We've been thinking about this failure dynamics mostly in science and technology, but it's mostly because we have a better data there. But if you think about the generic dynamics of failure, it could be something that's very widespread in terms of human. It also could be art, sports, culture, all kinds of human innovations. And it also could be biological if you think about the evolution. We learn so much rules about evolution by looking at species that went extinct rather than species that are still alive, which is the biggest failure you can define. Also thinking about artificial intelligence agents, reinforcement learning. The essence here is that you are, okay, I have failure now. Okay, so the essence here is that you let these agents fail in many different ways, so you know how do you design a strategy computationally that is more efficient. There is a long way to go, but we are very excited about this research agenda. Thank you.